lecture, we see the observations from experiments on photoelectric effect. This is the photoelectric setup, and today we are going to learn about the observation number 8. In previous lecture, we studied the frequency and stopping potential. What is the effect of frequency? If we changes the frequency of this monochromatic source, what is the effect of photoelectric current? In previous lecture we learned that, and today we are going to study about the stopping potential and incident frequency. What is the relation between stopping potential, that means we can vary the potential difference using these keys. Potential difference of what? This collector plate, and we are going to change different material, different metal of emitter plate. So by graphically, these are y-axis and these are x-axis. On y-axis we have taken stopping potential, and on x-axis there are incident frequency. So what happens when we are changing this metal of emitter plate? We know that this emitter plate, we selected the alkali metals like zinc, magnesium and other alkali metals, because from these alkali metals are sensitive to light, sensitive to photoelectric or sensitive to light. So we have taken these metals as an emitter plate. So if we take as a zinc plate here, zinc metal, suppose this A, metal A. What happens when the incident line or incident radiation is emitted on this zinc emitter plate? There are different metals having different types or different frequency of ejection of electrons. We are not changing the frequency of this monochromatic source, but we are going to change this metal emitter plate. So when we are taken zinc emitter plate, the incident of ejection of electrons, and when we plot the graph of this ejection of electrons for metal A, the graph is intersect, this incident frequency is like this. For next observation, we replace this emitter plate by magnesium. Then the ejection of electrons is different for metal plate B, that is we use here magnesium, and first metal plate G. For different metals there are different ejections, frequency of ejection of electrons is different, and this by graphically it shows that its process, its intersection of this graph or intersection of these two lines is different for this incident frequency, and their work function, this 50 indicates as the work function of the metal. We call it as a work function. वर्क फंक्शन म्हणजे काय ते आपण नंतर पाहणार आहोत, पण या दोन्ही डिफरंट मेटल साठी वर्क फंक्शन जे आहे ते वर्क फंक्शन काय असणार आहे, डिफरंट असणार आहे. सो फ्रॉम दिस ग्राफ when these for different metals the slope of straight lines were same but intersects on the frequency intersects on the frequency and stopping potential axis were different. Their stopping potential axis is different for different metals. Again, we use the different metal point. Say pi not 2 is also different. That means the frequency of ejection from the different metal plates is different. So ejection of electrons is also depends on the which type of metal we use in this setup. So this is the observation number 8, and it indicates that, listen carefully students, it indicates that stopping potential, this V naught indicates stopping potential as a function of frequency of incident radiation. Frequency of incident radiation for emitter mode of a different metals. Again I read the stopping potential, that means V naught. Stopping potential, that means there is a, in emitter there is current flow of electrons, or there is a zero current noted in this emitter. For that zero current, the voltage is zero. We call that as a stopping potential. So stopping potential as a function of frequency of incident radiation for emitter mode of a different metals. Emitter mode of different metals. This is the observation number 8. Observation number 9. The photoelectric current we call as a photocurrent. Photocurrent and number of ejection of electrons. Number of ejection of electrons. Number of ejection of electrons depends on intensity. Depends on intensity. Depends on intensity, but not dependent on frequency. But not dependent on frequency of incident light. Not dependent on frequency of incident light. So what is the observations? The photoelectric current is depend on number of ejection of electrons. Depends on intensity and does not depend on frequency of incident radiation. What it means? Suppose this is the emitter plate and this is the incident source of radiation, monochromatic source of radiation. We write as a photoelectric current, that means current observed in this emitter depends on the number of electrons ejected from this emitter plate, and it depends on intensity. Already I tell you that intensity, that means the power of that source, monochromatic source, means 20. For example, this source we use 20 watt, 40 watt, 100 watt. We increase the intensity of that source. Intensity ज्याला आपण मराठी मध्ये तीव्रता असं म्हणतो. फॉर एक्झाम्पल एका रूम मध्ये जर 20 वॅटचा बल्ब लावला असेल आणि नंतर तोच काढून आपण 100 वॅटचा बल्ब लावला तर त्या रूम मध्ये लाईट इंटेन्सिटी जी आहे ती काय होणार आहे, इन्क्रीज होणार आहे. सो इफ electrons from this emitter plate ejected instantaneously and collected by this collector plate. This collector plate having a charge plus, and we know that as the electrons is ejected, this collector collects these electrons, and these electrons are flow through this wire, and this can be noted in ammeter. Number of electrons flow gives us current. Now these electrons we call it as a photoelectrons. Therefore, current stored in this ammeter as a photocurrent. As the intensity increases, the number of electrons from this emitter plate also increases. And as the electron increases, the current in this ammeter also increases. That means it depends. Number of ejection of electrons depends on this intensity of this source. As we decreases the intensity, number of ejection of electrons also decreases, which gives the less photoelectric current in this ammeter. So this is the important observation of this experiment, that is the number of ejection of electrons depends on intensity of the monochromatic source which we use, and it does not depend, this photoelectric current does not depend on frequency of the electromagnetic radiation. That means we use different color light source having same intensity. That means we are going to change the frequency of the monochromatic source, and if we changes the frequency, we could not get the maximum photoelectric current because there is a less ejection of electrons from this emitter plate. So remember this observation, that is photoelectric currents increases as the number of ejection of electrons, and it depends on the intensity of the electromagnetic radiation and does not depend on the frequency of electromagnetic radiation. These are the important observations from these experiments, photoelectric experiment. So next point that we are going to learn, that is what are the reasons or what is the failure of wave theory to explain the observations from experiments on photoelectric effect. So, reasons or failure of wave theory to explain observations, to explain observations from the experiment. What are the reasons which cannot explain by wave theory of these observations? So, first point, that wave theory could not give us the explanation of these observations. So, first point is most of the observations could not. We see in this earlier point that there are total 9 observations from this photoelectric effect. From these 9 observations, most of the observations observations could not explain by the wave theory of electromagnetic radiation. Could not explain. Like first and foremost observation that there is an instantaneous emission. There is instantaneous emission of ejection of electrons. Ejection of electrons. Ejection of electrons on incident of light. This point could not explained by the wave theory. That is, there is an instantaneous emission of ejection of electrons as soon as the light is incident on the emitter plane. This point could not explained by this wave theory. Wave theory like this. This we call it a wave. And from this wave, we cannot explain as soon as light is incident on this emitter plate. As soon as light is incident or electromagnetic is incident on this plate, the electrons is ejected instantaneously. So this point could not explain by the wave theory. Instantaneous emission as soon as the light falls on this emitter plate, then the electrons is ejected instantaneously. So instantaneous emission of ejection of electrons on an incident of light. Next point, wave picture. Wave picture would expect that metal surface will absorb the incident energy continuously. Wave picture will expect wave theory जी आहे तर wave theory ने काय एक्सपेक्टेशन केलं होतं की as soon as the radiation falls on this metal plate on the surface of metal the radiation was absorbed. That metal surface will absorb the incident energy continuously. This is the incident radiation. And this incident radiation energy will absorbed by this metal surface. This expectation has done by this wave theory. All the electrons, next point, all the electrons near the surface. For example, this is the surface of a metal. This is the surface of a metal. All the electrons near the surface will absorb energy. These are the electrons near the surface of this metal. And these electrons close to that surface will absorb the energy. The metal surface will require reasonable times. That means this metal surface requires some time to accumulate sufficient energy to knock out or knock off electrons. The wave theory expectation that these electrons near to the surface will absorb this incident radiation energy, and these electrons have take some time to come out this surface. That means, for example, here is electron, and these electrons absorb this incident energy and take some time. It may be 1 second or 1 millisecond, and then it take out. Then it eject from this metal surface. That means the first point, that is this point, the electrons does not eject instantaneously as the incident radiation falls on the metal surface. These are the reasons that wave theory would not explain that the radiation are in the form of particle. These are the main point. As soon as the radiation is incident on this metal plate, the electrons has taken this energy. The electrons taken this energy, and by taking this energy, it takes some time to eject from this metal surface. That means, in first observation, we see that as soon as the radiation falls on this emitter plate, the electrons are instantaneously ejected from that plate. But the wave theory could not explain this concept that electrons is instantaneously ejected from this metal plate. But it accepted that. This wave theory accepted, or it is the exception that the electrons near that surface has taken that energy, incident radiation energy, and takes some time to overcome from that metal surface. So, instantaneous ejection of electrons does not accepted by this wave theory. These are the 3 points that points failure of wave theory to explain the observation of this photoelectric effect. Now, next point is work function of a metal plate or metal. Work function of a metal. Work function is denoted by the symbol phi0. This work function is denoted by phi0. So, what is mean by work function of metal? For example, this is the metal surface. And the electromagnetic radiation is incident on this metal surface. These are the electromagnetic radiation having sufficient frequency. These electrons, we know that metal having 3 electrons. Different metal having different number of free electrons in it. This metal having 3 electrons in it. These electrons are free to move inside. These electrons are free. For example, these are the electrons, and they are moved freely inside the metal. They cannot exit from the surface unless the sufficient energy is supplied to them. जोपर्यंत या इलेक्ट्रॉनला कुठे तर मेटल मध्ये जे फ्री इलेक्ट्रॉन्स आहेत त्या फ्री इलेक्ट्रॉन्सला जोपर्यंत सफिशियंट एनर्जी मिळत नाही तोपर्यंत ते इलेक्ट्रॉन्स त्या सरफेस मधनं इजेक्ट होणार नाहीत. So the minimum amount of energy, the minimum minimum amount of energy. Minimum amount of energy required to be provided to an electron to pull it out to an electron to pull it out of a metal from the surface is called as work function. It's called as work function of a metal. It's called as a work function of metal. So the minimum amount of energy, incident energy. For example, this metal having energy 20 electron volt. This metal having energy 20 electron volt, and the incident energy is 21 electron volt. Incident energy is 21 electron volt. These metal have a frequency mu naught. These metal having frequency mu naught, and the incident radiation frequency is nu. In earlier point, we see that nu should be greater than mu zero. Frequency of incident radiation should be greater than the frequency of the emitter plate or ejected plate. So mu should be greater than mu zero. At that time only the electrons is ejected from this metal surface. That means the minimum amount of energy, this incident radiation having only 1 electron volt extra energy. This 1 electron volt energy has sufficient to these 3 electrons to move or to come out from this metal surface. So the minimum amount of energy required to be provided to an electron. That means 1 electron volt energy is sufficient for these electrons to come out from this metal surface, and the electrons is ejected from this metal surface. So minimum amount of energy required to be provided to an electron to pull it out of metal from the surface is called as a work function. Is called as a work function of a metal, and it is denoted by phi 0. So work function of this metal is phi 0, and its SI unit is electron volt. SI unit of work function is electron volt, or we show it by symbolically EV. This is the SI unit of this work function, electron volt. So minimum amount of energy to eject the electron from this metal surface is called as a work function of that metal. And different metals having different work function. For example, potassium. Having work function. If this metal plate is a potassium, then its work function is 2.3 electron volt. If it is a sodium, if the metal plate is sodium, then this metal, sodium metal, having a work function of 2.4 electron volt. So we call it as a work function of the metal. So photoelectrons, from this experiment, photoelectrons were always emitted. Photoelectrons always emitted if incident frequency call it as a nu, or greater than nu zero. Nu zero, even if intensity was low. Remember these important points, student. If photoelectrons, these electrons we call it as a photoelectrons. So photoelectrons were always emitted if incident frequency is greater than mu zero, even if intensity is low. Intensity low असेल, कमी असेल तरी सुद्धा, फॉर एक्झाम्पल ह्या इन्सिडेंट रेडिएशनची इंटेन्सिटी लो आहे, पण त्याची फ्रिक्वेन्सी जी आहे, incident radiation frequency should be greater than the frequency of this metal plate. तर आणि तरच इलेक्ट्रॉन जे आहेत ते इलेक्ट्रॉन्स काय होणार आहेत, त्या मेटल सरफेस मधनं इजेक्ट होणार आहे. इलेक्ट्रॉन्स इजेक्ट झाले, इलेक्ट्रॉन्स मेटल सरफेस मधनं बाहेर पडले, तर आपल्याला तिथे फोटो इलेक्ट्रिक करंट जो आहे तो करंट आपल्याला ॲमीटर मध्ये पाहता येईल. हा एक मेन पॉइंट किंवा मेन ऑब्झर्वेशन आहे या एक्सपेरिमेंटचं. नेक्स्ट पॉइंट इज Einstein's postulates. Einstein's postulates of quantization of energy and the photoelectric equation and the photoelectric equation. What are the postulates? And postulates of quantization of energy. Quantization of quanta. Quanta, that means bunch of that particles. Bunch of that particles, and each particle we call as a photon. So Einstein's postulates of quantization of energy on and the photoelectric equation. So Einstein's proposed that under certain conditions light behaves. What are the consideration? Propose that under certain conditions light behaves as if it was a particle. If it was a particle. It was a particle, and this energy that means light energy, this energy, its energy and its energy is released, its energy is released or energy is released in the bundles or bunch of particles. This absorption of energy is in the form of bundles or bunch of small particles, and these bunch of small particles called as a quanta. Bunch of small particle called as a quanta. Quanta. particle we call as a quanta. And he, that means the Einstein's named this quanta, named the quantum energy. Einstein named this quanta as a quantum energy. Named this quanta as a quantum energy. Quantum energy of light. Quantum energy of light as a photon. Quantum energy of light as photon. Quantum energy of light as a photon with energy. This is the first assumption or first proposed point by the scientist Einstein. That is, under certain conditions, light behaves as if it was a particle and its energy is released. Particle energy, for example, light and its energy release or absorb. Light energy release or absorb in a bundles. That means bundles or bunch of small particles like this. This is the bunch of particles, and this bunch of particles Einstein called it as a quanta. And this quanta, that is the quantum energy of light, and this quanta we call as a photon. One particle, this is the bunch of particles, therefore we call it as a quanta. And from this bunch of particles, one particle we call, for example, this is the one particle, smallest particle, and this one particle we call as a quantum energy of light, and this one particle we call as a photon. What do we call it as a? We call it as a photon. Photon, that means one quantum particles, and these quantum particles we call as a photon. This because it comes from light, therefore we call it as a photon. So as a photon with energy, and this energy we are going to show the equation. E is equal to h nu. E is equal to h nu. E, energy of the quantum particles or energy of quantum. E is equal to h nu. Nu means frequency of incident radiation, and h is called as a Planck's constant. So this equation E is equal to h nu, we call it as a Einstein's equation, photoelectric equation. E is equal to h nu, and this equation we call this relation between particle energy E and the frequency nu, and h is the Planck's constant, and we call it as a Einstein's equation of a photoelectric, or it is also called as a photoelectric equation. So up to this point today we stop here. Thank you.